Welcome to the complete guide to system design, the definitive resource for every concept you need to design scalable, reliable, and highly available software systems. Whether you're preparing for a big tech interview or architecting production infrastructure, this video covers the full roadmap, core trade-offs, the CAP theorem, databases, caching, load balancing, microservices, message queues, and much more. Let's dive in. Every system design conversation starts with understanding three fundamental trade-offs. First, performance versus scalability. Performance is how fast a single request completes. Scalability is how well the system handles increasing load. Optimizing one can hurt the other. Second, latency versus throughput. Latency is the delay of a single operation. Throughput is how many operations per second the system handles, designed to maximize throughput while minimizing latency. Third, availability versus consistency. A highly available system responds to every request, even if the data might be slightly stale. A strongly consistent system always returns the latest data, even if it means rejecting some requests. When approaching any system design problem, start by clarifying requirements, estimating scale, defining the API, choosing a data model, designing components, and then identifying bottlenecks. The CAP theorem is foundational to distributed systems. It states that in a network partition, which always happens in real systems, you can only guarantee either consistency or availability, but not both. Consistency means every read returns the most recent write. Availability means every request gets a non-error response. Partition tolerance means the system continues operating despite network splits. And since network failures are unavoidable, you always need partition tolerance. So the real choice is between consistency and availability. On the consistency spectrum, weak consistency offers no guarantees, used in video calls and gaming. Eventual consistency says all replicas converge given time, used in DNS, Cassandra, and DynamoDB. Strong consistency says every read sees the latest write, used in banking systems. Cassandra and DynamoDB favor availability plus partition tolerance. MongoDB and HBase favor consistency plus partition tolerance. Traditional SQL databases favor consistency and availability in a single data center setup. High availability means your system is operational the vast majority of the time. It's achieved through two main failover patterns. In active-passive, also called warm standby, one server handles all traffic while a passive backup waits on standby, ready to take over if the primary fails. DNS is updated to point to the passive on failure. In active-active, hot standby, multiple nodes all handle traffic simultaneously. There's no downtime, but you need to handle write conflicts. Replication can be master-slave, where writes go to the master and reads are distributed across replicas. Or master-master, where both nodes accept writes and require conflict resolution. Availability is measured in nines. 99.9% means 8.5 hours of downtime per year. 99.99 means about 52 minutes. 5 nines, 99.999, is only 5 minutes of downtime per year and requires massive redundancy. DNS, the domain name system, is the phone book of the internet. When you type a URL, your browser first checks its local cache. If it misses, it asks the ISP's resolver, which queries the root name servers, then the top-level domain servers like .com, then the authoritative name server for the domain, which finally returns the IP address. Each step caches the result with a TTL, a time to live, so fewer lookups happen over time. A CDN, Content Delivery Network, solves the latency problem by storing copies of your static assets at edge servers distributed globally. Users get content from the closest edge node. There are two CDN models. Push CDNs, where you manually upload content to the CDN, best for infrequently changing assets. And pull CDNs, where the CDN fetches from your origin server on the first miss and caches it, best for high-traffic sites. CDNs dramatically reduce latency for global users and offload bandwidth from your origin server. A load balancer distributes incoming traffic across multiple servers, eliminating single points of failure and enabling horizontal scaling. There are two types by OSI layer. Layer 4 load balancers work at the transport layer. They route based on IP and TCP UDP ports. They're fast and protocol agnostic. Layer 7 load balancers work at the application layer. They route based on URL paths, HTTP headers, and cookies, enabling smarter routing like sending API traffic to one cluster and static traffic to another. Common load balancing algorithms include round-robin, requests are distributed in sequence; least connections, routes to the server with the fewest active connections; IP hash, the client's IP determines their server, ensuring session persistence; weighted round-robin, servers with more capacity get proportionally more requests. A reverse proxy differs from a load balancer in that it can serve a single backend. It adds SSL termination, compression, and caching. When you have multiple backends, the reverse proxy becomes a load balancer. Choosing the right database is one of the most consequential architectural decisions you'll make. SQL databases, or RDBMS, like PostgreSQL and MySQL, enforce ACID properties: atomicity, consistency, isolation, and durability. They support complex joins, have a strict schema, and scale vertically. Use them for financial records, order management, and anything requiring strong consistency and complex queries. NoSQL databases sacrifice some ACID guarantees for scale and flexibility. There are 4 main types. Key value stores like Redis and DynamoDB offer ultra-fast lookups by key, perfect for sessions and caching. Document stores like MongoDB store JSON-like documents with flexible schemas, ideal for user profiles and catalogs. Wide column stores like Cassandra and HBase store data in column families, optimized for time series and analytics at massive scale. Graph databases like Neo4j model relationships as first-class citizens, essential for social networks, recommendation engines, and fraud detection. Choose NoSQL when your data is unstructured, you need horizontal scale, or you're iterating rapidly on your schema. When a single database becomes a bottleneck, you have 4 main scaling techniques. Sharding partitions your data horizontally across multiple database nodes using a shard key. For example, routing users with IDs 1 through 1 million to shard A. This enables massive write throughput, but makes cross-shard queries complex. Replication copies your data to replica nodes. The master handles writes. Replicas serve reads. This dramatically increases read throughput and adds high availability. Replicas can be promoted if the master fails. Federation, also called functional partitioning, splits your single database into multiple databases by function: a user's database, an orders database, a products database. Each is smaller, faster, and can be scaled independently. Denormalization duplicates data across tables to eliminate expensive join operations. For example, instead of joining users to orders, you store the user's name and email directly in the orders table. This speeds up reads at the cost of write overhead and potential inconsistency. Caching is the single most impactful optimization you can make. The fastest request is the one that never reaches your database. There are 4 main cache strategies. Cache aside. The application checks the cache first. On a miss, it reads from the database and writes the result back to cache. This is the most common pattern. Write through. Every write goes to cache and database synchronously, keeping them always in sync. Write behind, or write back. Data is written to cache immediately and flushed to the database asynchronously in batches. Faster writes, but risk losing data if the cache crashes before flushing. Refresh ahead. The cache proactively refreshes entries before they expire, eliminating cold start latency spikes. Caching exists at every layer. browser caches, CDN edge caches, web server caches, application-level caches with Redis or memcached, and database query caches. The hardest problem in caching is cache invalidation, deciding when to expire stale data. Use TTLs, event-based invalidation, or versioned cache keys to handle this. A monolith is a single deployable unit containing all functionality. It's simple to develop and debug initially, but becomes risky to deploy and hard to scale independently as it grows. Microservices decompose the application into small, independently deployable services, each owning its own data and exposing an API. A user service, order service, payment service, and notification service can each be written in different languages, scaled independently, and deployed without affecting each other. The API gateway pattern places a single entry point in front of all services, handling authentication, rate limiting, routing, and SSL termination, so clients don't need to know about your internal service topology. Service discovery solves the problem of services finding each other. In client-side discovery, services query a registry like Console or Eureka and load balance themselves. In server-side discovery, the load balancer queries the registry, keeping clients simple. Microservices introduce distributed system complexity, network failures, data consistency across services, and distributed tracing. So only migrate when the monolith's pain genuinely outweighs the complexity. Systems communicate over several network protocols. TCP provides reliable, ordered, connection-oriented byte streams used by HTTP, databases, and email. UDP is connectionless, fast, and best effort, used by video streaming, gaming, and DNS queries, where speed matters more than reliability. WebSockets provide full duplex persistent connections over TCP, enabling real-time bidirectional communication for chat and live dashboards. At the API layer, three styles dominate. REST uses HTTP verbs get, post, put, delete to interact with resources. It's stateless, cacheable, and universally supported, but can suffer from overfetching or multiple round trips. gRPC from Google uses protocol buffers over HTTP2 for binary serialization. It's 10 times faster than REST, supports bidirectional streaming, and generates client code automatically, ideal for internal service-to-service communication. GraphQL lets clients request exactly the data they need through a single endpoint and strongly typed schema, eliminating overfetching and underfetching. Perfect for complex front ends with varying data needs. Synchronous architectures block the client until the server responds. When operations are slow, like sending emails, processing images, or charging payments, this creates poor user experience and tight coupling. Asynchronous architectures solve this with message queues. The server immediately returns a 202 accepted response, and a background worker processes the job independently. This decouples producers from consumers, buffers traffic spikes, and increases resilience. The most common queue patterns are point-to-point, one producer, one consumer, message consumed once, used for task queues and job processing. Publish-subscribe, one publisher, many subscribers receive each message, used for notifications and event streaming with Kafka. Priority queue, higher priority messages jump the queue, used for payments and alerts. Competing consumers. Multiple workers pull from the same queue in parallel. Perfect for video encoding or order fulfillment. Background jobs can be event-driven, firing when something happens like a user signing up, or schedule-driven, like cron jobs that run nightly reports. Tools include Kafka, RabbitMQ, Amazon SQS, and NATS. Even experienced engineers make these mistakes at scale. No caching. Every request hits the database even for identical data. The system collapses under load. Fix it with Redis at the application, CDN, or database level. Chatty I/O, making hundreds of tiny network requests where a few bulk calls would do. Batch your requests or use GraphQL. Noisy. Neighbor. One tenant's heavy usage degrades performance for everyone on shared infrastructure. Solve with rate limiting and resource quotas per tenant. Busy database. Performing business logic, calculations, or data formatting inside the database. Move logic to the application layer. Retry storm. When a service fails, all clients retry simultaneously, creating a thundering herd that crushes the already struggling service. Use exponential backoff with jitter and implement circuit breakers. Synchronous I/O, blocking the main thread waiting for database calls or HTTP requests. Use async await and non-blocking I/O, extraneous fetching. Selecting all columns with select star when you only need 2 fields. Always select specific columns and paginate large result sets. Monolithic persistence. All microservices sharing one giant database. Use database per service so schema changes don't break everything. You can't operate what you can't observe. Monitoring has 4 key pillars. Health. Monitoring continuously checks if services are alive and responding. Kubernetes. Liveness probes and Route 53 health checks are common tools. Performance monitoring tracks latency, throughput, and error rates using the RED method, rate of requests, error rate, and duration. Tools include Prometheus, Datadog, and New Relic. Availability monitoring measures uptime against your SLA and pages on-call engineers when thresholds are breached. Security monitoring detects anomalous access patterns and unusual data. Access using tools like AWS, GuardDuty, and CM platforms. Observability is built on 3 pillars. Logs for detailed event records, metrics for aggregated time series data, and distributed traces for following a request across multiple services. 3 reliability patterns every system needs. Circuit breaker. Stop calling a failing service after a threshold, return fallbacks, retry after a timeout. Throttling. Limit request rates per client with token bucket or sliding window algorithms. Return 429 too many requests. Bulkhead. Isolate components in separate thread pools so one slow service can't exhaust resources and crash everything else. And finally, design all your operations to be idempotent. The same call should produce the same result every time. Enabling safe retries without side effects. You've just completed the full system design roadmap, from fundamental trade-offs all the way to production reliability patterns. You now understand the CAP theorem and consistency models, availability patterns and failover, DNS and CDN, load balancing algorithms, SQL versus NoSQL databases, sharding and replication, 4 caching strategies, microservices and service discovery, REST, gRPC and GraphQL, message queues and async patterns, 8 performance antipatterns to avoid, and monitoring, circuit breakers, and throttling. These are the exact concepts that power systems at Google, Amazon, Netflix, and every major tech company. The best system designers aren't those who memorize patterns. They're the ones who deeply understand trade-offs and make the right choices for their specific constraints. Keep building, keep designing, and keep questioning every architectural decision. See you in the next one.